population growth, radioactive decay, bacteria growth, as well as investments are just some of the real-world applications of modeling with exponents. Hi, my name is Tom Atwater, and today we're going to investigate exponential growth and decay. Let's start with a formula for population growth. Exponential population model. If a population P is changing at a constant percentage rate R each year, then the population at time T is equal to the initial population, P sub naught, times the quantity 1 plus R raised to the power of T, where P of 0 is the initial population, R is expressed as a decimal, and T is the time in years. Now, if R is positive, then P of T is an exponential growth function with a growth factor of 1 plus R. If R is negative, then P of T is an exponential decay function with a decay factor of 1 plus R. All right, let's try this out with an example. Tell whether the function is an exponential growth or decay function and find the constant rate of growth or decay. All right, so what we need to look at then is the 1.09, because in the formula, that is our area where it's 1 plus R. So if 1 plus R is equal to 1.09, that means that R is equal to 9/100. Now, if R is 9/100, that means it's positive, so it's a growth function, and the growth rate would be 9%. Exponential growth and decay apply to any situation where the growth is proportional to the amount that's present. Exponential growth models can be developed in terms of the time it takes the quantity to double. Let's take a look at that. Determine the exponential function that satisfies an initial mass of 0.6 of a gram and doubling every 3 days. So we start off by writing then the population given the number of days, so day 1, day 2, day 3. And what we know is that the initial amount is 0.6 of a gram. And we know that it doubles every 3 days. So I'm going to put in times 2 because it's doubling. But now the question is, what does the exponent have to be? And the answer is, it needs to be the number of days divided by the fact that it takes 3 days to double. In other words, if I were to plug in P of 3, then what I would have is 0.6 times 2 raised to the 3 over 3. And of course, 3 divided by 3 is 1, which means, of course, 2 to the first power is 2. It doubles in 3 days. So that would be the exponential function that gives us doubling every 3 days. Exponential decay models can also be developed in terms of the time it takes the quantity to be halved, that is, for half of it to decay away. The time it takes for half of a sample to change is the state called the half-life of the radioactive substance. Let's work an example of this. The half-life of a certain radioactive substance is 14 days. There are 6 6/10 grams initially. Express the amount of the substance remaining as a function of time t, and answer the question, when will there be less than 1 gram remaining? So what we'll do first is we will write out what the formula is based on the information that we were given. So our formula, and I'll call it D for decay this time, and I'm going to use T for time. And what we know is that initially there's 6 6/10 grams. And now we know that it's going to halve every 14 days. So we're going to multiply that times 1/2 raised to the T over 14. And once again, you can see that if I were to substitute 14 days for T, the 14 over 14 is 1, and that would be 1/2 to the power of 1, and so we would have half of the initial amount remaining. Now, we could solve this algebraically by plugging in 1 gram over here and then solving for t, but let's use our grapher to do it. And that means that we would enter that equation into the grapher, press our graph key, and lo and behold, we would then have that this graph, which shows us the intersection with y equals 1, which is what we're interested in, is right over here, and we are told the x value, which of course is our t value in this case, which is the number of days, so it's just beyond 38 days. 38 and 11/100 days is what we would round it off to, and that's how many days it would take for it to go from 6.6 grams to less than 1 gram. Now, exponential growth is unrestricted. However, population growth often is not. For many populations, the growth begins exponentially, but then it eventually slows down because it begins to approach a limit to the growth, and that's called the maximum sustainable population. Let's work an example of this. Use the data in the table and logistic regression to predict the maximum sustainable populations for Florida and Pennsylvania. Graph the logistic models and interpret their significance. Here's the table, and one of the things that I want to point out in this table is that the year starts as 1900, but what we're going to do is we have to pick a year that we will start with that's year 0. And when you do this, you want to think about picking a year such that when you go to the grapher, you can get the entire graph in there. And by experimentation on this particular problem, we've selected the year 1800 to be the year 0. And what that means in terms of our scale is that 1900 is actually going to be the year 100 when we look at our graph, as well as it's involved with the equation. Now, it's not going to change our answers. It's just we have to realize when we've plugged it into the grapher and when we get our equation out and when we look at the logistic model graph on the display, that that's what's going on. So just to clarify, 1910 is then going to be the year 110. And of course, 1920 would be 120. Okay, so that explains how this would be used. Now we plug these in to our grapher, and when we do this, we will then run our scatter plot. And the scatter plot is, well, first of all, for Florida, we have the black line right here, which shows the regression model that I've graphed after the calculator gave me the equation. And of course, each one of these are the data points that the calculator plotted using scatterplot. Now, the red line is Pennsylvania. And again, that's from the grapher, and each of these plus signs are the data points there. Very quickly, you'll notice that it appears as though Pennsylvania is beginning to approach some kind of maximum sustainable growth somewhere between, and if you'll notice with my y-axis min and max, this is 5 million, 10 million, and this would be 15 million. So someplace between 10 million and 15 million, Pennsylvania appears to be approaching its maximum sustainable growth. But now, I redid the window because this wasn't enough for me to see the pattern. So let's take a look at the next one. Now we can see what's happening here. Pennsylvania is, in fact, out here beginning to reach its maximum sustainable growth. However, Florida, because this is the year 2000, is still in the midst of its growth, right? And it's not going to be till much later, towards actually the end of this century, that Florida is going to begin to approach its maximum sustainable growth. So that's the picture of it. Now let's look at the algebra of this by taking a look at the two equations that the grapher gave us back by running the logistic regression. So Florida, f of t, its maximum sustainable growth is 28 million. That's what that actually stands for, 28 million. Whereas Pennsylvania's maximum sustainable growth is right at a little bit over 12.5 million. And as we noticed, Pennsylvania is already approaching that value now. Florida still has almost 100 years or maybe 80 years before it begins to approach that. All right, so we can say that the limit as t goes to infinity of f of t is 28 million. So that's bringing in the idea of limits. And for Pennsylvania, as t goes to infinity, the limit is 12 and 579 thousandths million. Interpreting this, we say that the maximum sustainable growth for Florida is 28 million, and that the maximum sustainable growth for Pennsylvania is about 12.5 million. And they're already approaching that. Great job. Now, I want you to try a problem just like this. So, what I have for you is, using the data on the following slide, compute a logistic regression model for Arizona's population for T years since 1800. So 1800 is year zero. Based on your model and the New York population model that I'm about to give you, answer the question, will the population of Arizona ever surpass that of New York? And if so, when will that be? So the important thing from your New York N of T equation is to recognize what is the maximum sustainable growth for New York. And as you realize now, that would be the 19,875,000. That's important because that's what you're going to compare with the Arizona model that you're about to have the grapher calculate. And what that looks like is this. Here's the table. This is the data that you'd want to enter into your grapher so that it comes up with, and you don't have to do New York. I've already done that for you. So you're only interested in entering those two lists. And again, I will write out over here that what you're interested in is comparing your answer that you get for Arizona with the 19.875 for New York. So pause the video while you work in this problem. And when you're finished, restart the video to check your solution. Let's find out how you did. After you enter the data into list 1 and list 2, or L1 and L2, then you have the calculator apply the logistic regression. And remember that that is the stat button followed by the letter B, and then you add in L1, comma L2, and what you should have come up with is this particular function. There are the keystrokes that you enter, and then the display shows us right here that the maximum sustainable population for Arizona is 15,641,521, which means then, of course, that it will never reach the maximum sustainable population of New York, which was almost 20 million. So Arizona will never reach that. All righty. So what about the graph of this? We can take the information here and, of course, rewrite that in our logistic equation formula, and we would get a graph that looks like this. And what it's showing us is that the maximum sustainable growth is right up here at about 15 and 64/100 million, which means, of course, it won't reach New York. And that's going to happen sometime down the line, but we don't have the actual numbers on our graph, so we can't estimate when that would be. So that was a great example in a real-world application where we could compare populations with each other. So in today's lesson, we talked about exponential growth and decay and logistic growth with respect to populations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.